Thank you, Cloud Person. So welcome back. Seems like it's been a really long time. It's been a week since we last met. Hopefully, you took the time to decompress on Wellness Day. That was a pleasant surprise for me, to be honest with you. And today, the focus will be on the LCD display, which is a little bit different from all the other things we've been doing thus far. And we'll also talk about the other component, the DHT11, which is a humidity and temperature sensor. And so this is building up for what we're going to do this Friday, but we will also pivot in various sorts to start to talk about networking. And so if you have not done your Mac attack exercise, please do so, because you will not be able to network your Arduino board without the MAC address. So what I have planned through ITS is to have static IP address, and that will make sense if you haven't on Friday, if you haven't taken a computer networking course, but to get a static IP address, how you locate devices on the internet, or network cards more specifically, across a network, is through something called an IP address. And we can't do that unless we have the MAC addresses. So please make sure you're doing that. I treat you like the adults you are. I don't want to have a pop quiz with a MAC address or anything like that. So please just get it done. All right. So before we begin, we will go over the usual administrative bits. Homework number 1, which is survey design, is due this Tuesday, today, at the usual 11:59 and 59 seconds. And so the intent in having this particular module, survey design, as a group project is to have input from all the group members, right? Absolutely, the group, 4 or 5 people working together, is going to bring in for each person his or her unique perspective. And so I'm hoping to see that. But yes, it is a group project. Certainly things like the notebook and the reflection will be very different. But I am enterprising to assess that everybody is bringing something to the table, making a contribution, and also having his or her opinion valued by their team. Okay, so that's the homework. The reading has changed. Now, this is where I remove some of the scaffolding. I sort of step away and do a little bit less for you so that I can, quote unquote, teach you how to fish, right? When you do this sort of stuff, you're integrating various components. Many times there's not a textbook and you have to do what I call read between the lines. You're gonna get information about components from the data sheet, and that data sheet might be for the component itself or a very closely related component, because many of these things support a common protocol. And that's actually the case with the LCD screen. And we'll talk a little bit more about that in the subsequent slides. So you're going to be, for part of your reading, doing preparation for what the exercise will be on Friday to make sure you're looking at and gathering, finding, locating, what have you, information on the LCD display and the humidity temperature sensor. Okay, any questions about this? No questions? Due next week will be project 4 on Tuesday, a week from today, at the usual 1 second before midnight. I haven't finished writing that up. I will post that this afternoon, and it will be related to the stuff we're going to talk about today. So I know there was a question. About homework 1, yes. Okay, I don't have them all memorized. So what was question number 4? Say that again. Membership. Say it one more time. I'm sorry. Is this thing in? I have this one. So this is all about creating personas, right? And in order to create personas, you're going to collect data. And these personas, as we had discussed, are fictitious people, but you must be able to instantiate them or find them within your population. And so when you design your hierarchical population, it's your choice about whether you want them to be overlapping subgroups or non-overlapping subgroups. And it's your choice entirely, your design, for what those different demographics are. But part of our discussion was those visible attributes and the invisible attributes, because it's often those invisible attributes that can impact more someone's experience and therefore their needs more so than the visible attributes. But it's a tricky thing when you're questioning those things about surveys because they're invisible. Some respondents or potential respondents might not be as enthusiastic about revealing those particular attributes for whatever reasons. Now, that being the case, once you have the design of your population, pick a few archetypes from that population and talk about them. Because this whole exercise for doing the population design is purpose with helping you design your survey targets, right? Time, location, and number, right? And so after you've done your design, look at different types of individuals that might come or rise from your design. And it's entirely the design, it's entirely up to you. Okay? All right, to answer your question. Any other questions? Thank you for putting yourself out there. Usually I find that when one person has a question, about a third of your colleagues have the same question and they're feverishly writing right now. Okay. No other questions? Really no other questions? No? All right. Going once, going twice. I once went to an Amish auction and bought a whole bunch of saws and hammers that I didn't necessarily intend to. So going once, going twice. Nope. Oh, you're up dry. So you just, yes. No, I'm joking. You didn't even see. All right. Anyways, I digress. So project number 4 will be posted and it will be out on Tuesday. I mean, it'll be due on Tuesday at the usual 11:59 seconds. So, all right. When we last met a week ago, we talked about hierarchical population design, and we gave a bunch of demographic examples. And in our case, the target is so-called student life at Clark University and whatever demographics are wrapped up into that. And so the idea then is to use, as I said before, your population design to help you determine what the mechanics are about the execution of your sample placement. And so this sample placement refers to, as I said, time, location, and number. Because of the way the campus is structured, you might only encounter certain small pockets within your population, depending on when you do your sampling, where you do your sampling, and also if you have enough samples, and if you take stochastic computing with me next time I teach it, you'll learn that as you increase the sample size, you're more and more likely to garner information that is more truly representative of the population. Okay, and so we then said, all right, well, when you take a survey, you're collecting data, and we need to now talk about different forms of data. We began with so-called categorical data types. These are things that are arranged in categories, and we said that they don't have a particular natural ordering. Now, the wonky thing about this stuff is that for every rule or definition, you can find a counterexample. And for categorical data, the counterexample are those types of categories that do have a natural ordering. And the example we gave was movie ratings. They're categories, yes, but they do have a natural ordering. So just because something's a rule, invariably, you can go out and find some counterexample, some nuanced counterexample to that rule. Okay. Then we also talked about numerical data, things that are numbers. And these things, therefore, because they're numbers, they have a natural ordering associated with them. But again, the counterexample, you can use these numbers like car model year as categories, right? And so being aware of the different data types will help you choose both the visualization of interest as well as the types of functions over that data or statistics you might want to compute to tell you something about what's going on with the population. And now we also talked about scatter plots, and we said that scatter plots are a registering of that data on a Cartesian plane of some dimensionality. And those types of plots or representations for charting are important for showing you relationships between certain types of measurements. And we gave the example of college coach, football coach salary versus football team ranking. We also went to things like bar charts, and those bar charts could be counts or could be proportions representing distributions over categories. We also talked about pie charts, which represent part-whole relationships. And then we talked about line charts. And we ended with line charts, among other things. With this type of line chart, we can do a line chart in time, as this is the case here. We see registered along the horizontal axis, we have the months of the year. And on the vertical axis, we have temperature in degrees Fahrenheit. And with this line chart, you can plot multiple types of measurements for multiple locations in this case. And when you represent them alongside one another, it tells you something about similar behavior from the perspective of the type of measurement that you're taking. Okay, any questions about this? No? And we also, when we looked at the pizza chart, we said how having multiple visualizations can tell you something more than just a single visualization. All right. So then we talked about generally this thing called a population, and this population has ground truth governing numerical quantities we call parameters. So these parameters, the good news is that they're floating out there, and the bad news is that you don't have access to them. So what can one do when you're trying to understand the gross level behavior from a data perspective of your population? You make a mathematical guess, right? And this mathematical guess is a so-called estimator. And for reasons that we won't talk about in this class, you can choose an estimator in a way that it becomes a really good mathematical guess. One of the things it has to do with is the sample size. And so this notion of the sample mean is a good mathematical guess from data. You draw your samples and you compute the average or the sample mean that we're abbreviating as X bar. And when we do this, we can use this X bar that we know from our samples, that data we collect from the survey, we can use that as a good mathematical guess for the ground truth mean behavior of that measurement from within the population. We also talked about the variability or the spread of values. And one of the examples you might think about is temperature. Temperature can vary a lot or vary a little if you keep measuring it over some period of time. And so that's a really valuable type of measurement or summary that you might have about the behavior of your population. In the case of things like commute time, if you measure the commute time and there's a lot of variability, it means people are coming from very near as well as very far. If your commute time from your survey respondents has very small variability, it means it's very regionalized, that they're located relatively close to campus. And that could be telling you something like your campus is primarily residential and not very many off-campus or commuters, students. Okay, and so we use this mathematical guess S squared, the sample variance. And the sample variance, it was on purpose that we have a leading constant 1 upon n minus 1 times that sum of the squared difference between each measurement, xi, and the sample mean. This is a measurement of dispersion, and the reason for that 1 upon n minus 1 instead of 1 upon n is because this is the so-called unbiased estimator. It's a really good mathematical guess that you can confidently use in place of not knowing this ground truth dispersion measure or variability measure floating out in the population. Any questions about this? No questions? That makes sense? Okay. And so there's a problem though. Whenever you have atypical values from your sample, if you're computing things like the sample mean X bar or the sample variance S squared, an atypical value, be that a value that's much smaller than what is typical or much larger than what's typical, can really muddy up your results. It can so-called move or skew your results. And so that means, let's say if everybody at Clark University lived within 5 miles, but one person commuted from Rhode Island, right? Much longer drive, that one person is gonna take your small result for commute distance and it's gonna make it much bigger than it really is. And so this so-called instability is solved for the measurement of variability by the so-called interquartile range. And the quartiles, we said, are those data points that separate the points into quarters or 25% increment of the values over the total span of values that you measure. And so this IQR, interquartile range, we said, was the difference between the third quartile and the first quartile. And it just happens, and this property holds true, is that 1.5 times the interquartile range below Q1 and above Q3. In that range, you're going to get 99.3, I think it was 99.3% of all the values that you could encounter. Okay, any questions about this? Does that make sense? And so if you have data that's so-called wiggly, a lot of variability, you're better off using interquartile range as a measure of dispersion, or the median as a measure of central tendency, typical value, than you are using the sample mean and the sample variance because of that instability. Okay, any questions? No questions. All right. So let's get to the heart of today's discussion, and we'll begin with the LCD display. And so inside of our Key Studio kit, you'll see this thing, and it's a so-called 8x2 character LCD display. And if you look in some of the literature, some of the data sheets and stuff like that, sometimes they'll describe it as being white on blue, right? White is the color of the font, and blue is the background. And so this thing illuminates, and programmatically, you can display characters. Now, there are some LCD displays that will display symbols from some library symbols, but this one does not do that. And the 8x2 refers to the fact that you have 8 positions in each row going across, and there are 2 such rows for display. There are all sorts of form factors. There's 16x2, 16x8, you name it, somebody's manufactures it. But the important part for this is when we look on the left-hand side of this particular one, now some of them, when you look at them, they'll have these drill through holes and you're supposed to solder. These ones, they were kind of nice, and they added these header pins along the left-hand edge. Now, one of the things I'd like to direct your attention to is you see a number here, 1 and 2, and you see a number here, 13 and 14. That's the numbering scheme for the pins. And if we imagine these pins as consisting, and there are a total of 14 of them, consisting of 7 rows going across and 2 columns, we number the pins when we count them row major from right to left. So this is pin 1, that's pin 2, 3, 4, 5, 6, etc., up to 14. And so this right-hand column, your right, is all of the odd numbers pins. That's 1, 3, 5, 7, 9, 11, 13. And this left-hand column, your left, are all the even numbered pins, 2, 4, 6, 8, up through 14. Any questions about this? Make sense? Yes. Why? That's a great question. It's less expensive, and there are certainly larger LCD screens, but they've just chosen to include this particular one in the kit. If you go out on the internet, search around, you can find all sorts of sizes. There's no one standard, but this is relatively cheap as a part, but, and I'm glad you asked that, they all adhere to the same control standard. The only difference is we have more pins. Now, these pins include a data line, a data bus. And so the more real estate you have on the LCD screen, the more addresses for locating where things are going to go, the more complex the logic, and you pay for that with a higher cost. In addition, the data bus is bigger. In addition, from a form factor standpoint, if you have a larger screen real estate, that's more LED, liquid crystals you have to energize to light up, and that's also going to sink more power. And so if you were to design any kind of system that used the display, one of the huge considerations is the so-called power budget. You want to decide, do I run this off of the equivalent of 2 AA batteries, or do I have to run it off of something like a lithium polymer LiPo battery? And so that also affects, if something is mobile, it affects the amount of battery life that you have if it's a bigger power budget. So I can address the considerations about which type of LCD screen you would consider if you're building a system, but why they built this one in particular, or why they included this one in particular in the kit that I purchased for the class, because it's cheap. Because there are addresses involved. It implements a control standard. And so you can look up the spec for a different LCD screen, 16:2, and it'll have the same protocol. And that's why they do this, because you have to have certain pins available to implement this standard, regardless of how much real estate you have on the LCD. And it gets even more complicated if you have symbols, not just characters. All right, any other questions? Okay. And so I can't really answer that question completely. You'd have to contact Key Studio, and Key Studio will sell you bigger LCD screens, right? It's just this kit had that particular screen in it. So this is an example of a drill through version. And in that case, you'd have to cut your own wires, strip the insulator from them, and do some soldering to build your connections. Now, this diagram, this table, talks about the pins on the LCD connector and what these pins do. So going from 1 to 14 in our case, because we have 14 pins, pin 1 is ground, and that's usually the standard. Pin 2 is your supply voltage. Now pin 3, V0, is interesting. V0 accepts a voltage, and depending on the level of this voltage, that'll drive your backlighting. So the screen will either get brighter or get more dim. Now, why would you want to do this? For power considerations. And in fact, if you have like a smartphone, you can always turn down the brightness of the display, and that's going to preserve battery life. Okay. If we look at pin 4, so that's 1, 2, 3, 4, that's register select. When you control this particular device, it has one of 2 registers, and those registers will control one of 2 things. Whether you're going to store data, and that data invariably are the characters you're going to display on this device, or it's the command. You can think of this command almost like an opcode in assembly, right? It's going to drive the circuitry to do something, set up pathways, and then you have a clock signal that latches on your circuit to do something. So this pin number 4, RS, if it is high, a logic 1 or plus 5 volts in that pin on the device. So this is 1, 2, 3, 4, 5. If it's high, 4. Here it is, 1, 2, 3, 4, RS, register select. If it's high, logic 1 or plus 5 volts, I'll use those interchangeably as synonyms. It's selecting for data register. If it's low, 0 volts or logic false, it's going to select for command. It's expecting that whatever data appears on the bus is a command or opcode that you want to send to this thing. Pin number 5 is your operation. It's either read or write. That's pin 5 here. If pin 5 on the device gets plus 5 volts or logic true, it's going to be a read, right? So it's going to read whatever appears on the bus. And if it's a logic low, it's going to be a write. So it's going to update something on the LCD display. And that's typically used for commands. Now, if we look at pin 6, that's the enable signal. So that's 1, 2, 3, 4, 5, 6. And that enable signal, it's the clock signal. It's what you use to so-called latch on or enforce the execution of a particular selected command. And so here we see if you get a high signal, a logic 1, it assumes that the read operation is enabled, but you need a transition from high to low in order to enforce a write or to latch on a write. That means whatever appeared on the data bus will physically be written. So that clock signal or that enable is really a clock signal. It's how you force the device to actually step through the sequence of operations you've selected, the opcode, in order to implement it, to carry it out. Okay, any questions about this? No? All right. And so the last 8 lines, which is pin 7 through pin 14. So that's 2, 4, 6, that's 7, 8, 9, 10, 11, 12, 13, 14. Those are the data bus lines. And that's from least significant bit, data bus 0, through most significant bit, data bus 7. And so we're going to be using, for this exercise for the next project, we're going to be using the 8-bit data bus and not the 4-bit. You'll see in the Key Studio guide, there are 2 different ways you can do it. Okay, any questions about this? And of course, these data bus lines either accept a logic 1 or logic 0, true, false question. The most significant is DB7. And so if we look at the binary representation, 1, 2, 3, 4, 5, 6, 7, I always end up needing another square. This would be DB0, and that would be DB7 in your 8-bit representation. So least significant is DB0, which is pin 7, and most significant is DB7, which would be pin 14 on the device. Okay. Any other questions? No questions? All right. Okay. And so this is the wiring diagram, and I've sort of repeated some stuff because it makes it a lot easier to remember versus flipping back and forth. And so Key Studio, in some of the kits, you can buy an Arduino clone, but we're not doing that. But to be an Arduino clone, you have to have the same I/O pinouts, right? Because you're going to interface with the same daughter cards or build the same stacks. All right, so here we have a breadboard, and we have the 8x2 LCD display, and then we have the digital I/O lines for the Arduino or Arduino clone. And then this device is a potentiometer. To jar your memory, a potentiometer is a variable resistor, and it changes its resistance as you turn the dial on this particular device. If you've ever used, I don't think it's old school, but I'll say a high fidelity stereo system, or in your car, the volume knob, that's typically a potentiometer, okay? All right, and so here, one of the things we're gonna look at, of course, going back to what we talked about for the breadboard, here we have the positive rail for the breadboard, and we have the negative rail, and we're gonna feed that with ground and voltage, VCC, or plus 5 volts from the board. And so you see here, 5 volts from the board is going to the positive rail on the breadboard, and then ground, which is over here, is feeding. It's funny that happened right as I touched the screen. And then ground on the board is feeding the negative rail. And so it's entirely up to you which digital I/O pins on the board you're using for each one of the control or data pins on the device. But it'll be really important to manage that well. And so my recommendation to you is, before you change things, to actually look at the example as it is, and then wire it based on that example using number sign defines or variables for things so that you can change it as you please. Now, there's really no difference which digital I/O pin you use on the board to feed one of the signal or control lines for the device, outside of it looks nicer, right? You don't want to have wires kind of crossing and woven like pasta or something like that, because that'll make it physically harder to trace where things are, right? But it's entirely up to you which I/O lines, digital I/O lines on the board you use to drive the various signal and control lines on the device. And so one of the bigger kind of considerations is to distinguish between what these are, the control and data lines for the board, versus what pins you're using to either give it a logic high or a logic low or read, okay? All right, any questions about this? No? All right, so let's take a look at a couple of them. Well, we said that the 8 pins DB0 through DB7 is here. So that's pin number 7, 8, 9, 10, 11, 12, 13, 14, right? Starting at DB0. So here you'll notice DB0, this purple, starts at pin 3, and DB7, the orange here, ends at pin 10. So you have pin 3, 4, 5, 6, 7, 8, 9, 10, those 8 in sequence feeding DB0 through DV7, right? They're side by side physically on the digital I/O pins for the board. Okay. Any questions about that? That makes sense? And so this is just an aesthetics thing. But again, I'll repeat myself. I strongly recommend you follow what's in the example as a baseline. And then once you convince yourself about how it works, then you're free to do whatever you want, just to manage things a little, the complexity a little bit. Okay. So those are the data bus lines. And we talked about ground and 5 volts and voltage +5 from the board to the rails. Let's look at what feeds the device itself. So we said pin 1 is ground and pin 2 is +5 volts. And so here, pin 1 is the blue. You'll notice that's going to the negative rail, which is ground on the breadboard. Pin 2, that's voltage, VCC, or VDD sometimes it's called, and that has a jumper to the positive rail on the breadboard, right? So next, let's look at this variable input. So we have our potentiometer, and the potentiometer has 3 connections, one for ground, one for VDD, and one for the output of that variable resistor. So here we have ground from the potentiometer to the negative rail, that's ground. We have from the positive VDD to the positive rail, right? That's VDD. And this third one in the middle, this yellow wire in the diagram, that's going to be the output signal of the potentiometer. And so that output signal for the potentiometer is going to feed pin 3, which is V0, that variable backlighting power supply for the device. And so here we have the output voltage from the potentiometer in yellow feeding pin 3. So it's 1, 2, 3. Okay. All right. That's our backlighting. And if we, and I'm kind of belaboring this on purpose to give you an example of actually following some of these things. And so here we have register select. That's pin 4 for the device. So that's the purple, 1, 2, 3, 4. And that purple we see is being fed by pin 12. And then we have the read write, the operation selector, pin 5. So that's up here, that's the orange, and pin 5 is 11. Let's see, 11. So we have 11 feeding the read write, and we have 12 feeding the register select. And then for the enable, pin 6, the enable 2, 4, 6, that's the purple one over here. The enable is pin 2 on the digital I/O for the Arduino board. Okay, any questions? Does that make sense? So I would invest the time in looking through the materials, in convincing yourself into how it works, and exercising patience in tracing these connections. Okay, all right. So to make these connections from the header on the right-hand edge, let me see if I can bring it back up, on the device, it'll be useful to use so-called DuPont connectors. Now, a DuPont connector is not the same as a jumper, it's different. And the DuPont connector has a socket side, you see over here, and it has the pin side, you see over there. Now, the socket side, it's on purpose, is very useful for plugging in to the header that's along the left-hand edge of the device. Now, because these things are squared and not round, you can push them right flush against one another and easily mate them to these header pins for a nice tight connection. The other thing about the DuPont connector, and a DuPont connector is not the same as a jumper. You can see they look different. The jumpers, for one, have pin sides on both ends, whereas the DuPont connector does not. The jumper wires, they're not physically attached or affixed to one another. The DuPont wires, when they come in the box, you'll notice that they're kind of glued together side by side like a ribbon, right? Almost looks like what's called a ribbon cable. But it's easy enough to pull these apart. And so one really strong recommendation for protocol when you're building your circuit, because you have 2 columns of 7 connectors, I would recommend pulling off 7 DuPont connectors and make sure they're still attached to one another, because that'll form a nice ribbon, and you stick these flush to one another and push it down into your header, as one unit. Makes it a lot easier to do. Okay? All right. And so you're going to need glued together DuPont wires. You pull off a bundle of 7, pull off another bundle of 7. The first 7 handles the odds. The second 7 handles the evens. And you're going to have to pretend you're a surgeon or something like that and really kind of be careful. And maybe it takes a little bit longer than a few seconds, maybe a minute for some, but it'll be worth your investment in time to do that because it'll be really, really tricky to try to do it other ways. Okay? Makes your life easier. All right. Any questions about this? And so DuPont wires are fixed together in a ribbon and they're easily separated. And the other thing I found is very useful is that you keep this ribbon together and you pull apart the individual leads about halfway so that when this is plugged in to the header on the left-hand edge of the device, these can kind of snake around and plug into the various pins on the Arduino, okay? Or the digital I/O connections on the Arduino. All right, any questions? No? All right. And so this is the variable resistor. And as I said before, it has 3 pins on it or leads or connections, 1 for ground. And some devices, you'll see voltage called VCC, some you'll see VDD. It's the same thing, or they'll just say +5. They're all synonyms. And so we have, in this case, VCC in this figure and ground. And then we have our output, which is generally the center pin, but they're marked on the device. And this output pin, pin 2, is going to feed into signal line 3 on the device, which is V0 from the spec sheet, which controls the backlighting. Okay, any questions? No? All right, this is going faster than I thought. And so the other thing, and this was to Jeffrey's point, right? That this is double data rate random access memory, and you physically, inside of the driver software, you address each cell as a unique memory location, right? And so the other part that makes these things tricky, as they get bigger, you have more memory locations that you have to manage, right? And so here in this 8x2, we can see 16 addresses, and these numbers are unique and used underneath the covers to decide when I put character data someplace in ASCII code, where do I put it in order to display something on this LCD device, okay? All right, and so you won't be using it at this level. There are LCD APIs that come from Key Studio, and for that you'll be installing the library. And the library is in the form of a directory, and in that directory there's a properties file, there's a C++ file, and an associated header file. And it's that header file you're going to use through a number signing. Excuse me, your voice is going. Don't do this for a week and your voice goes. And there's a number sign include that you're going to use to pull in this header file so your program gets the definitions that are in the C++ file in bytecode. All right. And so this is the, I'll call an anatomy of the program for driving the LCD 8x2 display. And so you start out, you're going to include liquidcrystal.h, and that's found in the Key Studio library. You're just going to literally go inside that Dropbox folder that they link off the website. You're going to take the library's subdirectory, copy all the folders, and then paste those folders as they are into the library's subdirectory underneath where your Arduino IDE installs programs, okay? And so you're going to need those libraries, but in your program, you number sign include liquidcrystal.h. Now you notice here, there are angle brackets, and angle brackets are reserved in C++. Well, this is not C++, it's a subset of C++. In Sketch, I'll say more correctly, these angle brackets mean it's a system library. Because you've installed it underneath your IDE, it's a part of the system library, in contrast with your own library, which is a header file, a .h file, like we saw in the AHA alarm that you define, right? And so that's really, really important. This angle bracket underneath the covers it's going to look to the location where your system libraries are installed. And that could include system libraries for the operating system for things like networking and memory management, or it could be system libraries for the IDE environment. Okay, so that angle bracket is very important. Now, I like to include number sign defines because it makes the program self-documenting and makes it look pretty, right? Easy to understand what's going on. And so this baud rate that we use for the serial print, when you do your setup, I like to define it as a number sign define. Some people use variables, that's fine. But the difference is when you use variables, and I get to your question in just a second, when you use variables, that takes up what's called symbol space. Now recall, this microcontroller only has a really, really small, relative to your desktop or laptop, a really small amount of memory. And one of the things that your program, that takes up space in your program when you load it into memory are the symbols. Symbols are things like function names and variable names. And so my reason for using number sign defines is because after the preprocessor phase runs, this goes away. It's doing a replace of baud underscore rate with 9600. That doesn't have any impact on the runtime image size, your program in its executable form. But if you use a variable, that's now taking up space. So if you have a lot of stuff going on in your program, for a microcontroller, you want to be aware how much space is being taken up when you're represented as a runtime image. Your question? Oh gosh, I can't remember. It's the bit input output rate, but I can't remember what its acronym BAUD stands for something. I'm going to write it down, the question, and I'll look it up. But I remember when I was a little kid, they had these modems, and they were so-called acoustic coupled modems, and you dial a data line and you'd listen and you'd hear like this kind of chirping, like if you accidentally dial a fax machine, and then you put it down on this device that would listen to it. And those like 128 baud modems or 124 baud modems, and a baud stands for roughly the bit input output rate, but I'll get the actual, what the acronym means. The BAUD stands for something, but I can't remember. And if you're curious, spool, which I do remember, stands for serial peripheral operation online, right? Print spooler has a long history, but anyways, I digress. So I'll look that up. Let me write that down. It's not written down. It doesn't exist for me. So, okay, any other questions? No? All right. So we're using the 8-bit interface. So in many places in this program, you're going to need to know that you have 8 data lines on your data bus. And so here, this is from the example, and it depends on what your choice is for the pins for the Arduino. One of the things you'll notice here, well, the read-write is going to be pin 11 on the Arduino, the digital I/O line, and then the I forgot what it's called. The register select is going to be pin 12, right, on the Arduino. And then you'll notice here, when we said before, pins 3, digital I/O line 3 through 10 on the board serves DB0 through DB7, right? Least significant bit DB0, most significant bit, bit 7, is DB7, which is controlled by these digital I/O ports on the Arduino board. Could you do it a different way? Absolutely. This is just mirroring what's in the Key Studio example. And then the enable pin, that's our clock signal, right? We're going to use pin digital I/O port 2 on the Arduino to drive that. Any questions? So again, as we said, with the anatomy of a sketch, we have our includes, our defines, and our data structures or variables. And if you have a preference for a variable versus a define, I would err on the side of a define, because as your programs grow in complexity, there's going to be no overhead for symbol space if you use a number sign define. Okay, so this is a command that's implemented in the example. And the purpose of this LCD command write is it's going to send a command to the device to get it to do something. And those do somethings are all sorts of things, which I won't list here. There's stuff floating on the web for spec sheets for this type of device and they're a standard set of commands. And this is what I referred to when I talked about LCD control protocol, because these commands are standardized so that if you take a 16 by 2 or a 8 by 4 or any size LCD screen, it's going to be the same command opcodes. Okay. All right. Any questions? No? All right. So we start out, and of course, we set a variable. And the first thing we're going to do is we're going to select what register we're going to use, whether the command register or the data register. And then we're going to also select whether the operation is a read or write. So here we're establishing what behavior we want from the device. And so I'm not going to talk about the pins, but we're just going to say, take a command, right? Set it to be a command, because this is going to be writing something to the LCD screen. And then you also want to make sure it's a write operation. So these two together with the register select and the read write is establishing what you want to do on the device. Question? It is technically, but the issue is that because you're displaying things on the board, you want to set up the data and then give it a command to do something with it, and then set up the data and then give it a command. If you do it in the setup, that only happens one time when you power cycle. And so it really belongs in a routine, because you're going to be switching between sending it commands and giving it data. Yes. Yes. Well, when you say write something, write doesn't mean the data. Write means the command. And so, for example, one command is clear the screen, right? You clear the screen, and then you present the data, and then you say, write that data to this part of the screen, to that address. And so you have to do the writes and the reads interchangeably in different times. And the problem with doing it in the setup is that setup only happens once, but you want to do this multiple times, because at one point, and when we get to the giving it the data, you'll see the difference. At one point, you want to send it a command. At another point, you want to send it the data. Okay. And so it really belongs, I'm glad you asked this, in a behavior routine, because this device is different from others. Other devices we've seen at this up to this juncture, you set it up and then you just read from it, right? So once you set up, you're done. Here, you're reconfiguring it, doing different things while you're sending it data. And so you need to have it in a behavior routine. Any other questions? No? All right. And so you set up the registers in the operation, and then now you're going to push out the data. Now, how it was implemented in the example, and caveat, this is not the only way to do it, right? This is just what was in the example. And my purpose here is in mirroring what is in the example. So when you go off and look at the Key Studio docs, you'll say, that's why they did that. Kind of explain a little bit between the lines. And so here you were going from least significant to most significant, and it doesn't have to be least to most, because each one of those data bus lines has a different location on the device. So you could do most significant to least significant. You can do in the middle outwards, whatever makes you happy. But I'm mirroring what's in the example here. So we're going to loop from DB0 to DB7, its position here, and it's going to select each one of those IO ports specified in the array on the Arduino. And this is kind of nice because you can change this if you choose to rewire things. So that being the case, now we're going to take the value and we're going to push out the least significant bit of this value, one bit at a time, starting at DB0 to DB7. And each time in the loop, we say, okay, well, is that value a 0 bit or a 1 bit in the least significant bit of the value that I want to send out as a command? Now, once I do that, I right shift. So now I kind of push all the bits one space to the right, and then I push out that least significant bit. So it's 1 bit at a time, this value, but it's done by right shifting and only sending the least significant bit of the value. So there's two things I'm talking about. When I say DB0 through DB7, DB0 through DB7, That's on the device. That is, I'll draw on the board a little bit. That's the LCD screen. Now, here, I physically wired DB0, which is pin 3, digital I/O port on the Arduino. I physically wired that to this on the device. So it's really important to distinguish when you see this, because you're gonna be, oh my gosh, what are they doing? The least significant bit of the value that you're pushing out, the digital I/O port on the Arduino, and the bus connection on the device. You're gonna have to manage those three. Does that make sense? Any questions? A little confusing? Yes? Okay. So let me do that again. So we have our device, and I'm calling DB0, the bus for the device. If I put a value on that device, it's either going to interpret that value as a command or an ASCII code that it's being asked to display. Now, here's my Arduino. And my Arduino has a pin number 3, I/O pin number 3. That's on the Arduino. I just happen to be calling that in a data structure in an array DB0, because DB0 has a number 3 in it, the 0th position of that array. So I have a value, and that value exists in the memory of the Arduino. Oops, I meant to say mem. That value is a binary number. And so let's say if that value was the number 1010. So what I'm doing is when I want to send that value 00001010 to the data bus for the device, I'm doing it 1 bit at a time. And so I say, okay, we'll first send the 0, then send the 1, then send the 0, then send the 1. And I'm doing that on different I/O port pins on the Arduino, which are connected physically to different data bus lines on the device. Does that help clarify? Okay, so this is going to be more of a kind of study it than necessarily a lot of stuff to build, because there's a lot of different moving parts going around. There's the data bus for the device, there's the value in memory, and then there's the digital I/O port on the Arduino that you're using to send that value. And they just happen to be doing it 1 bit at a time. Do they have to do it that way? Absolutely not. They just chose to do it that way. Okay? All right. Any other questions? No questions? No? All right. So I'm glad I'm taking the time to go over this. All right. And so now, once I do the digital write, the bits of the value, in this case a command, is now actively energized on the data bus. Because when I say write this value, it's either high if it's a 1, low if it's a 0. Now I have 0 volts here, 5 volts here, 0 volts here, 5 volts here, right? Okay. So once I've done that, okay, I have selected that this is a command, so it knows whatever's on the data bus, send that to the command register, and it's going to be a write operation. So I want to bring this value in, store it someplace. Now I do, oh, all right, I was just kind of trying to be fancy here, writing the individual bits. Now I go ahead and implement my clock signal. And my clock signal says, if I want to do a write, I have to go from high to low. But at the moment, it's low. So I enable this clock, that enable pin, to be low for some period of time. I bring it high for that same period of time, and then I bring it low again. And it's on this high to low transition, that's when it pulls it in and writes it on the device, the LCD. And so here, this is a square wave. It's almost like doing pulse width modulation, but it's only one cycle, right? And so here, do a digital write to enable low. My delta t is 1 microsecond, not millisecond. It's microsecond. And typically, when you deal with chip speed clock signals, it's microsecond 10 to the negative 6, right? And that's slow compared to gigahertz, right? That's 10 to the negative 12. Yeah, 12 or, yeah, it's, I mean, nano. I think it's 12 or 15. But anyways, now this is the go ahead and make it happen. That's latching on this signal. Okay. Any questions about this? Yes, yes. Uh-huh. Ah, and so this 1010 is a command, and some commands are, depending on their values, clear the screen. And so in that case, once you latched this, whatever was written on the screen, everything would go blue, right? And that's the background. If it were put the cursor in this location, then you'd see the little underlying cursor start blinking in that new location on the LCD. And so it all depends, and that's a great question, on what this value is, because different values are going to make the board do different things. And so that's different from the data, and the data is the ASCII code that it's going to display. Because you send the data, maybe you clear the screen with this, and then you send the ASCII code for hello, and it displays hello in that location. Okay, and so it's always command, data, command, data, command, data. Okay, any other questions? No? All right, and so this is what the setup routine looks like with this particular program. We start out, and I like to set up the serial terminal. And so the usual that we talked about, serial begin and while not serial, right? And you'll notice here, saying baud rate kind of, makes it a little bit more readable instead of having 9600 here. And then what we're going to do is we're going to enable the pins as being output. And this belongs in setup because we only do this once. Because we're using digital I/O and we're only ever sending data from the Arduino in the direction to the device, everything's going to be output, okay? And so we set up that output for all of the pins, the enable pin, which was pin 2, up through DI, which was pin port 12, right? So everything from 2 to 12 on digital I/O on the board is going to be output. Okay, what we saw last week with the PIR motion sensor is that we did a pin mode input because we're reading something. Here we're doing output because we're only ever sending data to the device. Okay, so now it's typical with this type of device, our LCD, to give it a delay because you have to give it time for those liquid crystals to warm up and for the energy to make the electrons jiggle, and then they phosphoresce, and then you see the character on the screen. So you always need to delay to give the device time to respond. You can't just do this and do that and do that. The board's too fast for it to work. Okay, so now, and this goes to Jamie's question, now we're calling this LCD command write. We're writing a command to get the board to do something. This particular command, and this is in hexadecimal, it could be in decimal if you chose to, but every place when you look up the spec sheets, they always use hexadecimal. Maybe that's just the standard they've chosen. So this in hex 3.8 hexadecimal says it instructs the board to select it as an 8-bit interface. For this LCD screen, you can do 4-bit or 8-bit, an 8-bit interface, and then make it a 2-line display, right? 2 lines of 8, both of those 2 lines. And this last one, a 5x7 character size. That's the size of the individual character, how many pixels an individual, like a character. And you can imagine a rectangle that's 5x7, and you'll have 35 dots, and it's going to light them up differently depending on which character you're displaying. Some have a bigger palette of character sizes, so you can have like basically font sizes. Others do not. Okay, and so here we're selecting the interface and the character size setting the input mode, displaying, turning on the monitor, clear the screen, hexadecimal 01 clears the screen. And you'll see this clear screen happen every time you display something and you want to display something else, you clear the screen. And this goes to Jeffrey's question that the reason why we have it in the LCD command write behavior routine is because we're going to clear the screen and then send it more stuff to display and then clear the screen. Okay. And I won't talk about the other ones. Any questions? No questions? Does that make sense? Yeah? All right. And the best way to kind of get a handle on this is to tinker with it. So now this is where the behavior happens. And this is for, I wouldn't have written it this way, but again, I want to mirror the example that's there in the Key Studio tutorial documentation. So we start out, we clear the screen, and then we set the cursor position in the second block. And now we're going to write a message. And you'll notice here, when you do the data write, I'm missing a routine here. Set up. Okay, this is the main one. I forgot to go cover this routine. I think I have it in the next slide. I was expecting to see it here and not elsewhere. So we write the data, and you notice this is not a command. This is the data itself that's going to display. And you notice when we write the data, we're writing the data only 8 characters because that's all that will fit on a line, right? And so it gives the data A, B, C, D, E, F, G, H. And then you'll notice we delay afterwards to give it time to light up those liquid crystal pixels. So then we set the cursor position at the second line, right? That's another command. So you'll see the command write, that's the routine that we just talked about before. And this data write, we haven't talked about that yet. I think that might be an internal library. Let me see what the next slide says. And then now that we set the cursor position, we go ahead and write new data. Now this will be on the second line of the 8x2 LCD screen, LCD display. And so we do that, and then we have a big delay because we want to have time to actually see what's on the first line and the second line. This first delay, the small delay, was to give the device time to light up the pixels because it takes some time to do. Okay. All right. Any questions about this? That make sense? No? All right. And so now we write a couple of other things. You'll notice at the top, we have another command. This is to clear the screen and return to that 0 position, right? And again, we do a command, and then we give it data. Another command to clear the screen. We give it time to clear the screen because those pixels now have to power down, and we have the blue screen display. And now we write more data, test with lines. Another command, this particular one, now I'm expecting that. This particular one, it sets the mode for the screen such that it displays what was already in the data buffer, but any new data gets sent out. This is so you can overwrite parts of the screen based on what was displaying. And so we do that command, and we set the cursor position. Instead of at the beginning of the line, we set it in the middle of the line, right? So these commands can get very complex. And then we write some more data. And essentially what this write is doing, it's taking everything that was in the second half of this, and it's overriding these dashes with the numbers 1, 2, 3, 4. Okay. And that's something you'll actually see. I have a video to play. And so we change the command again, and then we write more data. Here, we're writing on the second line at the beginning of the line. It's going to say test, 2 spaces, and the word OK. And then we have a delay of 3,000. That might be too low on the screen for people in the back to see because we want to see both of the lines. That last delay of 3,000 milliseconds or 3 seconds is so that we can actually sit and read the 2 lines ourselves before doing something else with the screen. Okay? All right, any questions about this? No? Make sense? All right. And so this is going to be something that's going to be important for you to tinker with. And I have a video, hopefully Exascaler is, let me turn this volume up. It's attached to the laptop. shaky hand. And that's for the test program. And it was literally copy and paste of what's there, but then cleaning up some stuff like having number sign defines and things like that. Okay, any questions about this? No? So I strongly recommend first looking at the material, familiarizing yourself with the test program, and then tinkering with it, i.e. copying it, trying it out, convincing yourself as to how it works. Because one of the things we'll be doing with this is defining our own routines that clear the display right to the first line, and then another routine that writes to the second line, right? Using what you know from the test program that's given in the tutorial to write your own routines, one to write text to the first line, one to write text to the second line. And you can put that in a single function where one of the parameters is the line number 1 or 2. Okay? All right. So in the next, let's see, 3 more minutes, let's take a little bit of a quick look, and I'll pick back up with this on Friday in the interest of time, as I'd rather spend the right amount of time here to shed light on stuff that the tutorial does not talk about. We're going to talk about the DHT11 sensor. And so this is the one that's in the Key Studio kit, and it does humidity as well as temperature sensing. And the lab on Friday will tinker with all this stuff and kind of help get you going. This lab will be to display the temperature and the humidity on the LCD screen, right? And so we're going to add some complexity here. And this is going to be more kind of studying the stuff, but also a little bit of software engineering, right? It'll be really, really important to structure your computation appropriately in the sense, think, act, cycle using a finite state machine. And then within the states, you call your behavior routines. And some of your team is going to be developing some of that software. Some of your team is going to be implementing the hardware. And it's going to be really important with the tasking to first decide what the tasks are, and then assign tasks to individuals and sequence through when you think things should happen on a timeline. Okay, and we'll talk more about that on Friday. Yes, question? Yes. That's a great question. In fact, when I thought about it, you could kind of put your hand and breathe on it, but in COVID era, you could maybe get a cup of coffee or something, anything that might do steam. If there's hot water, I mean, I wouldn't bring this in the bathroom or, in the shower, but anything that does steam is good, or just a different room that might be a little bit more humid. Yes. Oh, there is. Okay. Mm-hmm. Okay. Okay. That's a great idea. I mean, I might just bring hot water, but if you kind of cover it up a little bit, it'll be a little bit more humid. We could just get a hot cup of something. I like coffee a little too much, but that's a great idea. So maybe, no, I'm not going to bring it. I was going to bring a Keurig and we'll keep, doing that. But it's not so much about changing the temperature humidity. It's like putting the sense, act, response, sense, think, act cycle together with a much more complex actuator, namely the LCD display. And it'll require you to implement some behavior routines. And so this is what the device looks like. It has 3 connections, one for positive, one for ground or negative, and one for the signal. And the signal is going to use a digital IO line in the input configuration. So you're going to be reading a value from this, but you're not going to read it as you have things like the PIR motion sensor. You're going to instantiate a class or an object And this object, when you trigger the read, it's going to have members that you can query for the values. Okay. And so this is an example connection. So we have the ground wire, we have the plus 5 volts, the VDD wire, and we have the signal wire. You're going to choose an IO pin. Now, the tricky part about this, you're only going to have one digital IO pin left over after you wire in the 8x2 LCD screen, right? So it's going to be fully packed, which is why people use the Arduino Mega platform, which has a lot more IO lines. You can run out of these things very quickly. And so this is an example of the code. We won't talk about the code. We only have about 2-3 more minutes, but let me go all the way to the end and I'll pick back up with this DHT11 sensor on Friday, in addition to doing some networking. Let me project prep. I'll talk about that. But this is the finished product, and it only has 8 lines of text. So I realize it says Internet of Thing instead of Internet of Things. A backlit. Okay, so I will end with that, and I'll see you all on Friday. Please get things in early, not late. Don't wait till the last minute, and I'll see you all Friday. I'll make sure to post URLs to the videos. Okay, I'll see you then.